In this video, I'm going to talk about the wavelet theory and application. And the wavelets are a powerful tool for signal analysis and signal decomposition and construction. So what is the wavelet? The wavelet is a family of wave packets given by this function where we have B, the scale parameter, and the A, B is the translation parameter, and the A, the scale parameter. A is useful to look inside the frequency of the component of the signal, and B is therefore the time resolution of the signal. Some key features of the wavelets. Wavelets are time frequency localized. There are multi-resolution decomposition, and excellent for non-stationary signal analysis. Some tools we can use to analyze signal with wavelets are, for example, continuous wavelet transfer, which is simple convolution of the signal and a wave packet. It is useful for analysis of time-varying spectral analysis. So we consider signals with a frequency depending on the frequency, and the oscillating and the transient detection of events in the signal. Discrete wave transform DWT is a discrete version of wavelet analysis where we consider the filter bank. So we consider the input signal and we apply wavelet transform, and then we come up with the approximation coefficients and the detail coefficients. The approximation coefficient give information about low frequency component, and the detail coefficients are about high frequency component of the signal. So for multi-resolution analysis, we have to decompose the initial signal in two components, where we have the scaling function for low frequency analysis and wavelet for high frequency analysis. Here is, for example, an example of hard wavelet and a Mexican hard wavelet. Here is the mathematical notation of the high wavelet, where we have a function, a stepwise function, which is defined between -1 and 1, and this is best suited for step-like or blocky signal, or abrupt transitions, binary or piecewise constant behavior. Typical real signal we can analyze with half wavelets are, for example, digital square waves, sudden voltage jump in the power system, for example, in the industry, packet loss traces in the networking, abrupt movement steps in the motion capture data, and block structured video frames. Simulate wavelets. It is an improved symmetry compared to the basis, reducing reconstruction artifacts. Best suits for signal requiring symmetric, low distortion reconstruction, speech and perceptual audio, smoother physiological measurements, and the typical real signal you can analyze with the simulates wavelets can be, for example, Riemann BE speech signals, keen EEG segment, or for resting state alpha, zero wave varying radar return, and the ultra thickness measurement. This is the scaleogram, which is the time scale representation of the intensity of the signal. We can will come back on this kind of representation of the signal in the time scale or the time frequency domain. The filter bank interpretation of the discrete wavelet transform. We consider the input signal and we pass through a low pass filter, and we have the approximation coefficients which give information about the component of the low frequency, and if we apply the high pass filter, we can come up with the detailed frequency so that we can analyze the composition of the component of high frequency in the signal. Here are some families of wavelets, but there are also more. But the most important are, for example, HAR, which is the best fit to analyze step-like signals, the Dobeshi for smooth signal, Simulets for symmetric construction, Wavelet for precision frequency analysis, and bioorthogonal for image processing, and the MER for theoretical and smooth, and Molet for oscillatory signals, and the Mexican HAR for peak and spikes, or like sharp bands. Shannon for ideal filters. Some applications, the applications of wavelets can be found, for example, in the signal processing domain, like audio denoising to remove noise in audio signals, radar and sonar transient detection, image processing, and texture analysis. Engineering and science, for example, seismology, structural health monitoring. Wavelet selection. To select a wavelet, you can be guided with this table. For example, Meyer is best fit for theory and spectral analysis, for example, spectral analysis, and the Molet wavelet can be used to analyze EEG signal, and the Mexican heart is best to detect the peaks in seismological signals. What is next? As application of this